300 million years ago, long before the first dinosaur evolved, the Earth was a global swamp world. It was a landscape of towering, bizarre ferns and permanent steaming mist. Navigating this dense undergrowth was Arthropleura. It was a heavily armored millipede the size of a modern car, winding its 8-foot-long body through the rotting vegetation. In the skies above, the apex predator was Meganeura. This was an insect with the predatory instincts of a hawk and a matching 2.5-foot wingspan. These giants represent a massive departure from the insects we live with today. To understand how they reach these dimensions, we have to look at the physical constraints that usually keep insects small. Take the Goliath beetle. It weighs roughly 100 grams and fills the entire palm of a human hand. In our current world, this is as heavy as an insect can get. The Atlas moth marks another limit. With a wingspan of about a foot, it represents the absolute physical maximum for modern aerial insect flight. Across millions of species and hundreds of millions of years, modern insects consistently stop at these specific dimensions. They are held back by a specific mechanical constraint in their biology. Most large animals, like mammals, rely on an active respiratory system. We use lungs to pull in air and a heart to pump oxygen-rich blood through our bodies. Because this system is pressurized and efficient, it works just as well for a mouse as it does for a whale. Insects don't have lungs or blood-pumping hearts. Instead, they breathe through a series of small holes on the sides of their bodies, called spiracles. These holes lead to a network of narrowing tubes called trachea. Because there is no pump, oxygen must simply seep into these tubes and travel to the internal cells on its own, a process called passive diffusion. Diffusion only works over very short distances. If an insect tried to grow to the size of a dog in our 21% oxygen atmosphere, the breathing tubes would have to be so wide that they would crowd out its own organs. The creature would suffocate from the inside out. During the Carboniferous Period, plants evolved a tough new material called lignin to build tall, woody stems. But for millions of years, the world's decomposers lacked the specific enzymes required to break that material down. As a result, dead trees didn't rot. They piled up in massive, waterlogged layers, locking away millions of tons of carbon deep inside the Earth. This created a planetary chemical imbalance. The massive forests continued exhaling oxygen through photosynthesis, but because nothing was rotting, there was no decomposition process to consume that oxygen and return carbon to the air. This broken cycle forced atmospheric oxygen levels to soar. Concentrations climbed from 21% to an all-time peak of 35%. This supercharged atmosphere effectively bypassed the diffusion limit. The air was so saturated with oxygen that it forced its way deep into an insect's tracheal tubes, fueling massive muscle groups that would normally be starved of air. The prehistoric air was also physically denser. This gave wings more substance to grip, providing the massive lift required for heavy-bodied insects like Meganeura to stay aloft with far less effort. For a brief geological window, the atmosphere itself permitted a scale of life that is physically impossible today. Passive breathers were transformed into high-performance predators. The era of the giants ended when fungi finally developed the enzymatic toolkit to dismantle lignin. For the first time in millions of years, fallen wood could actually rot. This restored the planetary balance, but at a heavy cost. As mass decomposition consumed the oxygen surplus, atmospheric levels began a long, irreversible decline back to 21%. As the air thinned, the physical laws of diffusion returned with a vengeance. Oxygen could no longer reach the center of an 8-foot body. The giants were effectively suffocating in the changing air. This wasn't a sudden extinction event, but a slow biological filter. To survive in the thinner atmosphere, these lineages had to shrink, generation by generation, until they reached the small sizes we see today. This leads to a fascinating question. If we were to artificially raise the Earth's oxygen back to 35% today, would the giant insects return to rule the planet? Likely not. The Carboniferous was a truly unique moment in time because the sky was an entirely empty ecological niche. When the first giant insects took flight, they had zero competition. Today, the skies are occupied by warm-blooded, active-breathing, and highly intelligent predators. A hawk or a falcon, with its superior metabolism and fast-processing brain, would easily hunt a giant cold-blooded insect before it could even react. While oxygen provided the physical requirement for gigantism, the absence of competition provided the opportunity. The era of giant bugs was a direct consequence of a specific planetary imbalance, one that is unlikely to ever repeat.